begin with a word of prayer. Dear Lord, thank you for this day. Please help us today as we try to understand this material. Help me as I present it. Amen.
Amen.
So we're picking up the end of lemma 5.5. So we just constructed the connecting homomorphism. So this next theorem here, theorem 5.6, we're essentially using that to go from this short exact sequence of complexes to just an exact sequence here of abelian groups. So this sequence itself is essentially just a consequence of the fact that we constructed the connecting homomorphisms. So this theorem is essentially proving the exactness of this sequence. So we have to show that the image of this homomorphism is a subset of the kernel of this, the image of this is a subset of the kernel of this, etc. So there's about 6 steps here. So for the sake of time, I'm just going to go over the first 2, but once you see those, the rest of them are pretty similar. So, proof.
You get a different marker, that one's trash.
So was the last one.
Yeah, it's okay.
Let's see. Try a different color.
They'll...
Purple with red marker.
Yeah, we'll see. Maybe, I don't know how long that one has to live, we'll find out.
In fact. Okay, that one's not bad.
Okay.
The fact that the color of the cap is different is concerning though. So, first step, we need to show that the image of the homomorphism induced from I is a subset of the kernel of the induced map P. So they say map induced by P, map induced by I. Because this is a functor, is equal to Pi. And then by the fact that this is exact, this composition has to be 0. So this is equal to 0, aka 0. And this shows us that the image is contained in the kernel, since when we apply this map to the image of this homomorphism, we get 0. Does that make sense? Alright. So, second part here. The rest of them are pretty much like the second one. I just wanted to show the first one because I thought it was neat. So, the second one here is going to be similar to the others. So, here we're showing kernel, the map induced by P, is contained in the image, the map induced by I. Of course, actually, technically, there should be n's and -1s here, so these are actually different maps.
Yeah.
But I'll choose his notation. So, the map induced by P of Z plus boundary, so this is a coset here, is equal to PZ, then this is another coset, is equal to B prime prime. In other words, we're assuming that Z plus P is an element of the kernel of this map. So if we have that, since this is a short exact sequence, P is surjective, right?
Right.
So that tells us that there exists I guess he's using S prime prime such that...
So is he using D or partial? Because he's got You got partials now.
Um,
But then he's got the D on the. I think that D's supposed to be a partial, no? Am I
Which
missing
D?
something here? Why is there a D and a partial? There's a D in the middle of the.
The D is the homomorphism that we found in the last one.
Oh, okay.
The connecting homomorphism.
Oh. I'm an idiot. Go on,
Partials
Nathan.
within the complex.
You're fine.
okay, so
It's
since
just
this,
me.
since this is surjective,
As usual.
there exists an S prime prime such that S prime prime is equal to PS. Hang on, what is S though? Did you actually define that? Or I guess. Oh no, sorry,
Yeah,
I'm missing a step
you-
here.
you
That's why I
skipped,
get
skip
confused.
the sentence
So before that happens, right? Because Z is in the kernel of this map, that tells us that PZ
Right.
is equal to the boundary of some S prime prime. And then because P is surjective gives us an S such that S prime prime is equal to PS. Right, because this tells us that this is a boundary. So then we have PZ is equal to boundary PS, which is equal to, by commuting these,
Mm-hmm.
it's going to be P boundary S. So then we have,
Ooh.
I guess we're subtracting this
Yeah.
from this. So that implies, since P is a homomorphism, that P of Z minus partial S is equal to 0. So now he says, by exactness, there exists an S prime with I of S equal to, okay, so,
Kernel of P is the.
right, so this is contained in the image of I, which is injective. So that's why there exists an S prime.
Right, because the Z minus partial prime prime S is in the kernel of P.
Right.
So it must also be in the image of
The image of I.
I. Okay.
Yeah.
So you have IS prime equals to.
Partial S. So
Is prime.
S prime?
Is prime. That's what it says.
IS prime is prime.
Yeah.
It's a joke.
Oh, okay.
It's a sad joke.
Is prime?
Yeah, I'm sorry.
Okay.
I'm sorry, Nathan.
I thought you were telling me this should be prime, and I'm like, no, it's S prime. Okay.
Sorry, I'm an idiot.
So let's see here. Note that S prime is a cycle. Why is that? So we have
Guess he's about to show it now.
I partial S prime commuting, so we get I partial S is equal to partial Z. Okay, so I think he's skipping a step there. He's using this relation, right? So, oh, I just wrote the same thing, didn't I?
Yeah. So,
Okay, now it makes sense. Because now we use this, so he skips a step, but it's equal to Z minus partial S.
Yeah.
And then partial 0,
Mm-hmm.
so this is just equal to partial prime Z. Which is equal to 0 because that's a cycle. And since I is injective, partial
Right.
S prime,
If it maps to 0, it had to be 0.
and why is that?
That's
S
in-
prime was,
Because it's a homomorphism, so the only thing that maps to 0 is 0 if it's injective.
Okay, yeah,
Yeah.
makes sense. So,
It's a low hanging fruit. I picked it. Can't
therefore,
prove this. But
reduce map z plus b is equal to, oh, this should be s. Is equal to is prime plus b, which is equal to z minus partial s plus b, which is equal to z plus b. So, what does that tell us? Well, this here was in the kernel, and now we've shown it's in the image of the map induced by I. So, yeah, like, this proof here, I can kind of see what he was saying with the diagram chasing being more straightforward.
mm-hmm.
The one I'm going to get into later today will be less straightforward.
Ah.
So, let's see.
So those are the first 2 of 6 steps, but
Right.
that ultimately gives you the exact triangle, which you should draw
Right.
up in
yeah.
the upper corner,
So,
perhaps. I don't know.
And never erase it.
Yes.
So it was kind of confusing to me because like this is an actual commutative diagram. It's really like you could kind of draw this as a spiral if you wanted to,
But, if you
but
take
they
off
draw it
the-
as a triangle.
Take off the subscripts.
Right. Yeah.
Anything's allowed.
So.
So you take his triangular spiral and squash it to a triangle by
right.
removing the subscripts.
So
Projection of diagrams.
D. Map induced by P. H. So this is why it's called the exact triangle, because of this mnemonic diagram they're calling it. And so essentially this is just to remember exactly how you get the sequence, because you start at H of, well, I guess you start at, I guess it doesn't matter. You start at Hn of S prime, and you go to S along I, along P, you go to S prime prime, then you're back to
That's right.
S prime again, but you've gone down 1. So it's not exactly the same because you're going from Hn of S prime to Hn minus 1 of S prime, which
I
is
see.
why it's kind of like a spiral.
Cool.
So that's just sort of remember how to recreate this annoyingly long sequence I had to draw. Right, so our next theorem is naturality of connecting homomorphism. 5.7. So we have assume there is a commuting diagram of complexes with exact rows. Zero, S prime, S prime prime, 0, and on the bottom we have T prime, T prime prime, 0. With these morphisms in the middle here. Then there's a commutative diagram of billion groups with exact rows. So again, sort of like here, we're going from an exact sequence of complexes to an exact sequence. Here we're going from, well, I mean, this is essentially a chain map from these two exact sequences of complexes. And we're going from this to a chain map of just a a single exact sequence, I guess. I don't know how you'd say that. I'm probably saying that wrong. But there is a commutative diagram of abelian groups.
It says the naturality of the connecting homomorphism. So.
Right.
Hmm.
Actually, surprisingly, I don't have any categorical comments here. Yeah, I don't see exactly where the naturality is coming from.
Hmm.
I guess from this diagram commuting? I don't know. Oh, what am I doing?
I guess it's just that you get the same thing for the complexes as you do for the corresponding abelian groups.
Right. Luckily, the proof for this is pretty short, so it doesn't matter that this diagram kind of large.
With the understanding you use the connecting homomorphism, which is
right.
A slightly complicated beast that took us some time to understand last time. I mean, it is natural. It's like, what else could you do? But it's also like 5 things put together with a inverse image, which it's.
Oh, you know what it is? So each one of these is a chain map.
Mm-hmm.
But this entire collection here is a chain map. So you're going from these 3 chain maps with these 2 exact sequences of complexes,
mm-hmm.
and you're going to a single chain map between these 2 complexes here, which are the complexes we got from this theorem. So it's essentially the same thing, just we got 2 of them now. So this is going to be like Hn of T prime, Hn of T, Hn of T prime prime, Hn minus 1, T prime, etc. So proof of this, well, I guess it is short, but I still need more room than that, so I'm going to erase some stuff over here.
Cool.
And I'll leave the triangle up there. Yes. So, exactness of the rows is theorem 5.6, which is what we just did, so that makes sense. The first 2 squares commute because Hn is a functor, right? Oh, I guess I should have drawn these. This here is J, this is Q, this is D prime. Well, let's see. Where does that commute?
It's kind of iffy.
Oh, okay. Because we're going from here. So, okay, I didn't draw these in. This is I, this is P, this is J, this is Q. So, by assumption, these commute. Therefore, since this is a functor, this is just the image of this diagram under the functor. So these first 2 squares also commute. Which makes sense, because it's essentially the same thing. Then we have the connecting homomorphism here. So this is what we really need to show. So how they do that says, just to use some notation, this is going to be our first complex, the one on top, S star comma partial, and our second one is just T star comma, oh, look at that. Does not use
Simplex.
partial prime there. He actually uses a different symbol. What a concept. Yeah, if it were up to me and I actually took more detailed notes on this, I would replace all the primes with something like this instead. Make my life easier. Alright, so
Would it?
I don't know. I guess that's debatable.
Mm.
So let's see, what are we trying to show? So we need to show that
D prime. F.
d prime of f prime prime is equal to f prime of d, right? So if we look at f prime
Mhm.
of d, class of z prime prime, where z prime prime just some cycle,
Uh-huh.
then that is equal to f prime d of the class of ps, some f, s. So that's because p is surjective.
Mhm.
And then that is equal to f prime of the class phi inverse partial s. And so that's because, if you remember from last time,
There's a P inverse and a P that can.
right, yeah, because we had d was equal to the class of I inverse partial p inverse, so if you make that replacement here, the p's cancel, you're just left with this. So then next step, we just use the fact that j, f prime, and fi commute. So then this is equal to the class of f prime, I inverse partial s, which is equal to the class of j inverse f partial s. So then next step here, f is a chain map, so we can commute these two. So that's equal to class j inverse delta fs.
Well, Nathan, I thought that last step was iffy, but I've actually decided it's a jiffy.
Okay.
Wow.
Thanks for your pun.
It's getting worse and worse.
Alright, so what is this next step here? So then this is equal to d prime times the class q of fs. They say since
It is the
d
lowest.
prime.
The
So
lowest.
they're just using the definition of d again, but
Yeah.
with respect to the d for the other complex, essentially.
With T.
So they say since d prime class, then for the cycle here they're using zeta. Zeta prime prime is equal to the class of j inverse delta q zeta prime prime. So I think that makes
Q
sense.
inverse.
Q inverse? Here.
Yeah.
Thanks. So then we get,
Kind of going
what
backwards
does it do
now.
next? So I guess he commutes it again. D prime class f prime prime ps is equal to, yeah, he's pulling it out of the class now. So like you said, that's going backwards. So we got, this is just by the definition of the induced map. And then the last step, what does he do? That's equal to b prime, f prime prime, class, oh, that's just
PS is
because
C.
these are equal.
Crazy.
So, what does that show us? Right. We got
Yeah.
this.
But the class of Z prime
We
prime
got
was
this.
arbitrary. Woohoo!
Yay. Okay. So there's that.
Golly.
So. Okay, so now we have a definition.
You know, to me that proof seems very unnatural.
Hmm.
I mean, I
Yeah.
guess it's a natural proof, but I don't know, you just look at it, it's like, what?
Yeah. I mean, it's pretty much just shifting through the definitions for the most part, and applying commutativity and stuff.
I mean, if I give you some tattered clothes,
Surjectivity.
if I give you some tattered clothes and put you on a street corner and have you write that on a wall, people will give you money. For sure. Do you think?
All right. So if A is a subspace of X, then we define the nth relative homology group which we denote Hn of Xa is defined to be the nth homology group of the quotient complex of the singular complex of X, quotient singular complex of A. So this is like what I was saying last time, where we use the quotient complex. So this is kind of interesting. It's sort of like we did with fundamental group. We're finding, instead of just homology, now we have relative homology groups. So these next two theorems are kind of technical, but we're going to use them later. So theorem 5.8, should probably erase some stuff. Otherwise I'm going to run out of room. I'll erase this stuff over here. Alright, so theorem 5.8. So, let's see, if A is a subspace of X, A subspace X, I keep looking at the wrong one. Then there's an exact sequence Hn of A, Hn of X, Hn of Xa, and then from the connecting homomorphism, Hn minus 1 of A, and so on. So, moreover, F, I guess this is just a continuous map from X comma A to Y comma B, where I guess B has to be a subspace of Y here. Like they're kind of using the top squared, like we did earlier. Then there's a commutative diagram. So this one, this one gives us the exact sequence and the chain map. So that's pretty nice. We get a lot of stuff for free. And proof here, they say, is immediate from theorems 5.6 and 5.7. And I looked over this for quite a bit. I, for the life of me, could not figure out how they did that. See, because my thought was, if you look at this short exact sequence of complexes, right? If we could find a short exact sequence of complexes like this, then it would be immediate from theorems 5.6 and 5.7. But it's the then here that I couldn't quite figure out. Because here you can just use the inclusion. And then, that's injective, so that's nice, that's what we want, because if it weren't injective, then this wouldn't be short exact. The issue is here. The other natural choice would be the inclusion. But if you do that, I don't know, let's call it J, then this is not surjective. But it needs to be surjective for this to be a short exact sequence.
Oh, you just do J cross inclusion.
What do you mean?
The Cartesian product of the map J and the inclusion map. What is x comma a? That maybe I maybe jumped on the gun here.
Yeah, so if x comma a is like s star of x mod s star of a, right?
Oh, never mind.
Didn't you already explain that it was exact?
This?
Yeah.
I don't know, he might have. I might have missed it. Where was that?
On page 90.
Let's see.
Oh, that's like forever ago. Oh.
Oh, okay. Yeah, I guess that's it, because this was defined to be
Okay.
S star X or S star A. Okay, cool. Thanks for pointing that out, Daniel. So then, we can actually say now it is immediate from theorem 5.6 and 5.7.
Yeah.
Because theorem 5.6 gives us this.
I was
Theorem
describing
5.7 gives us this.
I was describing a map into the Cartesian product of x and a. You could use the identity on x cross the inclusion.
Yeah, see, I think that was my issue too. Like, I was thinking just in terms of the topological spaces.
It's not inclusion, it's the
But the fact that
projection.
this is a quotient here, that makes that surjective,
Anyway,
so that makes sense.
That has nothing to do with what you're doing, so I'll shut up.
Yeah.
And so like the f primes are all kind of like the f prime, the f prime prime that we would need are all kind of like the different forms of f. One of them's like in 5.7 we have like 3 different maps.
Oh, these.
So,
You haven't
Right.
read them yet, I don't think.
Wait, did I?
well here's like
5.7.
yeah.
Wait a minute. Oh, you're on. Oh, there is no name to these vertical maps in here. Well, he says they're induced by f.
Right. So I'm saying like here the different f prime and f prime prime, like one of them is just like the regular f from x to y. The other one is like the restriction of f at a.
Then you
And
can
then the other one
compose
is,
with the natural quotient map. Okay. Okay, cool. That makes sense too. Yeah, so then 5.8 automatically gets you this then. Let's see. So 5.9. Actually, what time is it? Because whether or not I get into this. let's see, how long is this one? Oh, this isn't bad. I'll go through this one. Because they say this is also implied by some sort of super long diagram chase. But I don't know why anyone would ever want to do that when the proof they give is a lot easier. Or at least assuming you've done their exercises. I guess that's why it's shorter. Because this actually uses the version of third isomorphism theorem for complexes. So it's actually an interesting proof as well. So theorem 5.9. Now we have a triple of spaces, x, a prime, and they're contained in each other. So if we have this, then there is an exact sequence then there is an exact sequence hn a prime hn xa prime hn xa finally d hn minus 1 aa prime, etc. Moreover, there's commutative diagrams of pairs of spaces. So if this commutes, then there's a commutative diagram with exact rows. Essentially the same picture that we've had for the past two proofs, but I'll try it again. And I guess it's slightly different. So you've got different rows, but
It's 3:00 p.m.
I think I'm getting better at drawing these. At least I'm figuring out how to do them faster. I don't know if they're more legible. They're probably not. But, alright, so proof here. Actually, since we're kind of running out of time now, maybe I'll just say it. But if you look, let me see where it is, on page 91, the third isomorphism theorem says that if you have three complexes that are contained in each other, so if you have U contained in T, contained in S, then there's a short exact sequence of complexes, T star U, S, U, S, T, 0, where then they have some, well, they give you the maps here, but I don't think that matters for this proof, so I'm not going to write it down. So essentially what they do is, let's see, I guess to get these, they take the simplicial complexes of these three spaces, and then they use that to get this short exact sequence, and they do the same thing for these.
Right.
And then they applied theorem 5.6 and 5.7 again. So that's
Yeah,
pretty
'cause if they're
straightforward.
subspaces, the complexes are subcomplexes.
Right.
Yeah.
Yeah, I don't think we've explicitly proved that, but
That was
I
one
just
of the
think that's
like,
true.
that was one of the like lists of things that he put since it's
Okay.
like an abelian group.
okay. Yeah, that makes sense. Alright, so after this he has some remarks. Like I said, he says you could prove that by doing a diagram chase as well. Another interesting remark he makes here. First off, one we're going to need to know is that Hn of x, comma, the empty set is equal to Hn of x. So the notion of homology group is a subset of the notion of relative homology groups. And we're actually going to use that later, so keep that in mind. Then he also mentions that given the content of this theorem here, you could actually define a functor from top squared into comp, essentially by setting S star xa just to be the quotient complex of x and a. Then he also argues that the induced map given by gamma n maps to induced map on gamma y, or gamma n. But this is well defined because the induced map on the simplicial complex of A is contained in the simplicial complex of B. But that's not relevant to what we're doing. So I just wanted to mention that. I thought that was interesting. You could also have a functor from top squared. So now we get to the 5 lemma. This is the fun diagram chasing I was telling you guys about. So I'll just get into it. Theorem 5.10, 5 lemma. So if you have the following commutative diagram with exact rows, with rows exact,
5 lemma.
then
Yes. The
1 if F2 and F4 are surjective, and F5 is injective, then F3 surjective. So this first part here, well, these first two parts are known as the two 4 lemmas.
Uh-huh.
So this
Yeah.
is 4 lemma part 1. And so I'm not even going to write down the second one. If F2 and F4 are injective and F1 is surjective, then F3 is injective. Actually, it's dual. So from a strict categorical sense, we only need to prove this one anyway. But regardless, just this is a super long diagram chase, so...
Time for a new marker. That one's dead. He lived a good life, though. It did good work.
So, regardless, just based on time concerns, I would only do this one anyway. And so...
Is he not going again next time?
Let's see. Proof, he just says
I think
parts
you're going
one...
again next time anyway,
I
right?
probably will anyway, but
Yeah.
by duality, the second one follows, so... Yeah, and proof here, he just says parts 1 and 2 are proved by diagram chasing.
You're supposed to be an expert on it by now.
Yeah. So, I mean, the thing is, I literally looked up the proof on Wikipedia.
Mm-hmm.
I have no shame. But at least the proof that they used was completely different from the proof that we saw today with diagram chasing. So maybe there's different ways to do it, but I don't know.
Hmm.
But I might need a lot of space, so I'm going to erase this stuff. Oh.
It's too late. What's done is done.
No. The exact triangle.
Now General Zod is freed.
Alright, so I'm going to do an alternate setup here because I liked the labels they use on Wikipedia better. Whoa, did I? Oh, okay. Yeah, so they used, this is like the first four parts of it. So you got B, C, D, D, B prime, C, D prime, E prime, M, N, P, Q, G, H, J, S, T, U. So let me keep another color marker handy here so we can keep track of the direction we're moving in. That works. Alright. So, again, we want to show that if M and P are surjective, and if Q is injective, that implies that N must be surjective. So our first step, to show this is surjective, we want to take an element C prime in C prime. So since P is surjective, there exists a D, element D, such that P of D is equal to T of C prime. So C prime, of course, well, D, of course, is here. So let's see. By commutativity, U of PD is equal to Q of JD. So that's, wait, where is UPQJ? So we're using the commutativity of this square. So then, since by exactness, the image of T is equal to the kernel of n.
What is F3 in your
F3 is
F3?
N.
your F3 is N?
Yeah. Because he kind of like took off the first.
Yeah, I'm just trying to translate. So your F3 is N. So you're trying to show N is surjective. So
Right.
you start by picking a point in C prime,
Right.
which you called
C prime.
C prime. Oh, okay.
Then we took a point here in D, and because P is injective or surjective, there exists a D in D such that P of D is equal to T of C.
Very good.
So you're moving here back
Okey-doke.
up that way,
Very
and
good.
by commutativity, we're moving like back this way.
So you got U.
So far we've kind of like
U of P.
swung back that direction,
So you
sort
got
of.
U of P. U. Go on. I'm just thinking.
So here we used the commutativity of this square. And then the image of T is equal to the kernel of N. Wait, did I write that down right? Image of... This should be U prime. Or, not U prime, U, I suppose. Because there is no U prime.
So P of T.
So this is by exactness, because we're given that this is exact. So are you following now? Which part are you stuck on?
I'm getting there. I'm just trying to figure out where P of D is. P of D is in
P of D is in D
prime.
prime.
D prime. And then you say U of P of D is equal to Q of J of D.
Used to.
I gotcha.
Okay.
Yeah, I'm with you.
So, now we have U of T of C prime
It's equal to 0.
is equal to U of, oh, I think you're ahead of us, but that's where we're going.
Yeah.
It's equal to Q of JD. So then, because Q is injective, J of D is equal to 0. So D is an element of the kernel of J. Or in other words, by exactness, the image of H. Therefore, there exists a C, element C, such that H of C is equal to D. Thus, T of N of C is equal to P of H of C is equal to T of C prime. Now this part I thought was interesting. Now we subtract this from this and use the homomorphism property. So that implies T of N of C minus C prime is equal to 0, which implies this is in the kernel of T. See, at this point here, like when you actually get into it, you can kind of see what they mean by like each step is dictated by the last.
Yeah.
But at the beginning, it's kind of like, okay, what do I do first? So, what's the next step? Oh, I don't know why I started writing that.
Kernel of T is the image of S? I don't know. Is that what you use?
Well, it's in the kernel of T. Yeah. So, is that what they do next? Yeah, so this is in the image of S. So there exists B prime and B prime.
S of B prime equals to...
Will be. So, to to recap,
But S of B prime is also equal to C prime minus NC, right?
right.
I mean, that's the connection between what you're doing and what you're writing.
Well, now by commutativity,
I mean, S of B prime is equal to C prime minus NC, right?
so B prime, C prime image of
So what you wrote there, the last thing you wrote, I think, is the surjectivity of M. Which is true.
I guess, is this equal to M of B?
Well, the point is C prime minus NC is in the image of S, right?
Yeah.
So I'm assuming you would say S of B prime is equal to C prime minus NC. Now it's also equal to M of B because B is a B, M is a surjection, right? So there exists a B and B that well, I don't know why you write that actually. Maybe I missed it.
What is?
I mean, you've proved that C
M
prime
is over here.
I'm just saying you proved C prime minus NC is in the kernel of T, right? Which is in the image of S. And then you say there exists a B prime.
Hang on, I think I might have been skipping a step.
Yeah,
There exists a B prime.
I think you're just supposed to say S of B prime equals to C prime minus N of C. Unless I'm missing something deeper.
Yeah, I think I skipped a step.
And I'm not saying anything terribly profound. Oh, you didn't have to erase all that.
So, such that S of B prime,
Yeah.
C prime minus N of C.
Yeah, that's it.
So now, okay, yeah, I skipped ahead one line. Now, since M is surjective,
Right.
there exists a B element B.
Oh, so you can
That's
write.
not confusing at all.
Oh, so you can write B prime as M of B. Is that the idea?
Right.
Okay.
So now, by commutativity,
Aha.
we have N of GB
Yeah.
is equal to
S
S of M.
S of M of B.
So we got
N of G.
these two commute.
Yeah. Ah, now you come back to C at last.
So
It was a long.
N of GB.
This is like a typical vacation of Dr. Sprano, right?
Is equal to C prime minus
I'm going to Florida by way of Colorado.
N of C. So now we got this again. So,
Cool.
oh wait, hang on.
N,
So we move this over.
N of
So we get
G.
N of G of B minus N of C is equal to C prime. In other words, N of GB minus C. Hey look, we found our element. And we're done.
So it's surjective.
Yes.
Yeah. And you do have to agree, like what he says, like once you take a step, the next step is given for you. But
Yeah.
and there probably are more than one
Yeah,
way to do
I'm
this.
kind of
The point is you got to use the data somehow, and like
right. Yeah. Yeah, just kind of like weird. Like we had to go over this way.
see, we really should do
then
these in
back
Math
here.
200 because if people did one of these in Math 200, they would really understand surjectivity and injectivity. Just one of these problems, right?
Good luck with that.
Not even once.
Yeah, they don't pay me enough.
Okay, so part 2 is dual, and part 3, which is implied by parts 1 and 2, if F1, F2, F4, F5 are isomorphisms, then F3 is an isomorphism. That's what time we got. So yeah, I've got like 10 minutes. I can probably do next page.